Welcome to the deep dive. We sift through the research, we cut through the jargon, and we try to bring you something really truly mind-bending. Today, we're tackling a question that could, well, potentially redefine everything. What if the universe, its dimensions, its forces, even the particles we think make it up, what if they aren't fundamental? What if they actually emerge from something, well, deeper, more subtle, something based on resonance? What if reality is less like a set of rules and more like a song?
That's a really potent way to put it. And it leads us right into today's topic. We're diving deep into a paper that's genuinely groundbreaking. It's by Philip Randolph Lilien from the UCTE Research Institute, just published August 2025. The title is FCHP Coherence Eigenstates. And what it does is introduce a completely new derivation within this framework called the Finsler coherence hyperfractal phase space, FCHP for short. And this isn't just, another interesting theory. It's presented as a major step towards a unified coherence theory of everything, UCTE.
Right, UCTE. So our mission today for you is to really unpack this. It's complex, no doubt, but it's absolutely fascinating. We'll explore how this FCHP framework seems to weave together hyperfractal geometry, something called gauge emergence, that's where fundamental forces come from, and this core idea of coherence resonance, all under this huge umbrella, the unified coherence theory of everything. And when we say huge, we really mean it. This isn't just a small step. This paper has been formally classified, get this, as a Tier V foundational ontological breakthrough. It scored a 9.3 out of 10 on something called the Eureka scale, which is, well, that's the top tier. So honestly, prepare yourselves. We're talking about potentially rethinking what is a genuine paradigm shift.
Absolutely. To really get why Lilien's FCHP work is so significant, we need to first understand the bigger picture it fits into. That's the unified coherence theory of everything, UCTE. Now, UCTE starts with a really radical premise. It challenges our standard view. Traditionally, physics kind of assumes the universe's structure, its particles, its forces. They all come from fixed laws of space-time, almost like cosmic commandments set in stone.
Yeah, like a blueprint. But UCTE just flips that completely on its head. It introduces this idea that I find, well, almost beautiful, that everything originates not from fixed laws, but from resonance-driven coherence processes. And these processes are embedded in something even more fundamental, a hyperfractal manifold. So if you're used to thinking, particles are the basic building blocks, it's a massive shift. UCTE says, nope, coherence, not particles or forces, is the primary reality. It's like saying the melody is more fundamental than the notes, or the instruments playing them. The harmony, the pattern, the resonance, that's the real thing. The notes only make sense within that tune. It's like the universe is singing and the song itself is the fundamental truth.
Precisely. And the ambition here is staggering. That's why it's called a theory of everything. It's described as the master ontology unifying geometry, physics, biology, and consciousness under coherence dynamics. Ontology, that's the study of what fundamentally exists. So UCTE isn't just proposing a new physics, it's suggesting a foundational framework for, well, all existence. It implies a single explanation connecting space-time, curvature, life, maybe even thought itself, all through coherence and resonance.
Okay, so if coherence is primary, if it's the underlying melody, then the huge question is, how does the stuff we actually see, gravity, light, matter, us, how does it emerge? How does it come into being from this abstract hyperfractal manifold and its resonances?
That's the big one, right? And this deep dive into FCHP Coherence Eigenstates, Lilien's specific work, promises an answer, a surprising one, linking the abstract to the observable.
Right. To start grasping that emergence, we need to rethink geometry itself, the very description of space. So let's talk about the geometry FCHP uses. Traditionally, especially in Einstein's general relativity, we use Riemannian geometry. That assumes space-time is basically uniform, isotropic, like a smooth, even fabric, same properties everywhere, whichever way you look. And it works incredibly well for a lot of things. But FCHP says, not so fast. It uses a Finslerian structure, which is fundamentally different and, frankly, way more interesting. Forget the smooth, uniform fabric. Imagine space-time is more like a tapestry where the weave itself changes depending on where you are and which way you're looking. The texture, the direction of the threads, it all varies. So the rules of geometry, how you measure distance and curvature, they aren't fixed. They depend on both your position and your direction.
Mathematically, this is captured by a metric that depends on both position, let's call it x, and directional orientation, let's call it y, gij. This directional dependence is key. It allows for what the paper calls anisotropic resonance pathways. If the geometry itself isn't uniform, if it has preferred directions, then coherence, those resonant patterns, will propagate differently depending on the direction.
Anisotropy. Direction matters. unlike the uniform symmetry of Riemannian space. And this is absolutely crucial for the next step, right? The dynamic emergence of dimensions, this varying weave, these preferred directions, they create the conditions for new layers of reality to actually unfold.
Exactly. Which brings us to a really core, kind of mind-bending concept in FCHP, hyperfractal dimensional emergence. So in this view, dimensionality isn't fixed. It's not like we just have 3 + 1 dimensions set in stone. And it's also not like string theory where extra dimensions are maybe curled up, compactified, hidden away. Instead, dimensions emerge dynamically via coherence reduction.
Dynamically emerge. What does that actually mean in practice? How does that work?
Well, it means the number of dimensions you can actually observe or interact with isn't constant. It can change. It reveals itself based on how coherence organizes itself. Think of it like shifts or accumulations in the levels of coherence.
Okay, like imagine a landscape hidden by fog. As the fog clears in patches, maybe because the coherence level changes, like temperature shifts, clearing fog, new structures are revealed.
Yeah.
Hills, valleys, new dimensions. So FCHP models this using coherence gradients within this manifold, where coherence builds up or shifts. Dimensions literally unfold. They become manifest.
Precisely. It's a process of revelation driven by the self-organization of coherence. The potential was always there, perhaps, but it wasn't coherently expressed. And the paper uses this analogy of hyperfractal dimensional layering. We know fractal self-similar patterns, complexity at every scale. Think coastlines, snowflakes. A hyperfractal manifold extends that idea into these emergent dimensions, layers upon layers, each potentially fractal, each dynamically appearing or receding.
Oh, wow. Okay, so if space is like that, infinitely complex, dynamically shifting dimensions, our standard calculus isn't going to work, is it?
Yeah.
Classical calculus assumes smoothness, integer dimensions. It's like trying to measure a fractal coastline with a straight ruler. You miss the essence.
Exactly right. It's fundamentally inadequate for this kind of structure. And that's where the need for fractal calculus comes in. It's the mathematical engine needed to drive this theory. It extends classical calculus to handle differentiation and integration over these incredibly intricate, non-smooth hyperfractal structures.
How does it do that? What are the tools?
A key tool is the fractional derivative operator, often denoted as I. Unlike standard derivatives, which have integer orders, first derivative for slope, second for curvature, etc., fractional derivatives can have non-integer orders represented by that index alpha. This allows them to capture the non-local, self-similar properties inherent in fractals. It's a math designed for this kind of texture. So if you want to describe how coherence evolves in this space, you might use an equation involving this operator acting on coherence eigenfunctions. Think of eigenfunctions as the specific, stable patterns of coherence that can exist. The equation might look something like sal alpha psi lambda alpha psi. Here, Deitel psi is the fractional fractal derivative, sal is the coherence pattern, and lambda alpha is a coherence eigenvalue.
Okay, eigenvalue. So that's like a specific value, a number associated with that stable pattern.
Exactly. It's a value that quantifies that particular state of coherence. But here's the really wild part, connecting back to the dimensions. That fractional index alpha in the derivative operator, the theory proposes it directly tracks the activation of hidden dimensional layers.
Wait, so the order of the derivative, that fractional number alpha, acts like a dial that tunes into different dimensions.
That's the proposal. As alpha changes, it's like you're probing different layers of this hyperfractal structure. And the eigenvalues, the lambda alpha, they then parameterize how coherence cascades across these hyperfractal dimensional layers. They effectively measure the coherence level associated with each accessible dimensional configuration. Changes in alpha lead to changes in lambda alpha, potentially triggering phase transitions where dimensions emerge or recede.
So the math isn't just describing it, it's literally encoding the dimensional unfolding.
Yep, theory.
Yeah, that's mind-bending.
It is. And building on this, the paper derives these coherence eigenstates. These aren't just any patterns. They are defined as stable resonance modes within the FCHP manifold. Specifically, they're called curvature phase attractors. Think of them as the naturally preferred, stable ways coherence can organize itself within this dynamic anisotropic geometry, like the natural resonant frequencies of a complex instrument.
Okay, attractor. So coherence kind of settles into these specific states.
That's the idea, and they emerge directly from the Finsler geometry. The Finsler curvature tensors, which describe how this direction-dependent space bends, are key, because the underlying connections, the gammas in the math, depend on both position and direction. The resulting curvature spectrum naturally splits. It decomposes into these phase-like eigenmodes. Each stable eigenmode corresponds to one of these coherence eigenstates, one of these attractors. The geometry itself generates the stable patterns.
Now, you mentioned these aren't quite quantum states like we usually think of them, not probabilistic wave functions.
Right, that's a crucial distinction. The paper describes them as quasi-geometric resonance states, where phase continuity replaces traditional probabilistic wave functions. So imagine stable, deterministic, geometric patterns of resonance woven into the fabric of space itself. Not probability clouds, but definite, coherent structures. It suggests a universe potentially more deterministic at its core, governed by geometric coherence rather than inherent probability.
Less like rolling dice, more like a crystal forming precise patterns.
That's a good analogy. And mathematically, Lilien proposes a variational framework to find these states. Essentially, you set up an equation, aleo medo pf plus lambda r opodaya, which looks for the most stable configurations. It involves a Lagrangian F that couples the Finsler geometry with the coherence patterns. Solving this yields specific, discrete eigenvalues, lambda, which correspond exactly to these emergent stable coherence eigenstates. These are the allowed resonant frequencies of the universe, according to FCHP.
Okay, that's the setup, the geometry, the math, the eigenstates. Now, what's the big payoff? You mentioned gauge symmetries, the fundamental forces.
Exactly. This is where FCHP potentially delivers a huge breakthrough. In conventional physics, the standard model, we have gauge symmetries, U1 for electromagnetism, SU2 for the weak force, SU3 for the strong force. They dictate interactions, but often we have to sort of impose these symmetries onto the theory, and then we have to break them using mechanisms like the Higgs field to give particles mass. It works, but it can feel a bit tacked on.
Right, like you build a framework and then add the symmetries, then fiddle with them to match reality.
Precisely. But here's the punchline from FCHP. Those coherence eigenstates, the ones derived naturally from the Finsler manifold's geometry and resonance, they provide a natural origin for gauge symmetry sets U1, SU2, SU3 without assuming spontaneous symmetry breaking.
Whoa. Okay, hang on. So the rules governing electromagnetism, weak, strong interactions, they just fall out of the geometry. They're not added in.
That's the claim. They arise intrinsically from the stable resonance patterns allowed by the Finsler structure, a huge simplification. The theory directly maps these geometric resonance states to the forces. U1 symmetry maps to the electromagnetic coherence phase, SU2 maps to the weak isospin phase, and SU3 maps to the chromodynamic phase.
So light, radioactivity, the force holding nuclei together, they're fundamentally different stable patterns of coherence within this geometry.
Yes. They're described as resonance reductions of a deeper coherence manifold. The gauge fields themselves, the electromagnetic field, etc., appear as phase-selected eigenstates of the Finsler curvature operator. It's a fundamental link. The geometry dictates the allowed resonances, and those resonances are the fundamental forces.
That establishes this deep geometric field duality you mentioned earlier.
Exactly. Two sides of the same coin. Coherence curvature, how the space is shaped by coherence, is dual to field amplitude, the strength of the force. And dimensional fractality, the complex layering of dimensions, is dual to phase quantization, the discrete quantum-like nature of the fields.
So the shape and structure of space is the origin of forces and quantum behavior. They're not separate things happening in space. They're aspects of the space's coherent structure. That's genuinely profound. It feels less like physics and more like discovering the universe's operating system.
It's a deeply unified vision, and that profound nature is why it receives such a high rating on the Eureka scale.
Right, the Eureka scale. You said 9.3 out of 10, Tier 4 foundational ontological breakthrough. Let's unpack that rating. What makes it that significant?
Well, the Eureka scale within the UCTE framework isn't just about clever ideas. It measures fundamental shifts in understanding reality, our ontology, our model of what exists. A Tier 4 rating, the highest, means it's not just adding a detail, it's restructuring the foundations. Think Darwin, Einstein, the quantum revolution, discoveries that change the questions we ask.
And FCHP gets that rating
because it fundamentally restructures the ontology of geometry, coherence, and emergence. It proposes a new ontology of physical law reality emerges from coherence resonance encoded in the Finsler manifold structure. Laws aren't external, they arise from the system's dynamics. That's a radical shift from fixed, immutable laws. And it sits at the intersection of three revolutions. First, the ontological revolution. Coherence is primary, not particles. Eigenstates are resonance attractors. Dimensions, fields, forces, they all emerge from the manifold. They aren't pre-imposed.
Second, the mathematical revolution. using fractal calculus on a Finsler manifold. This isn't just a tweak, it's a necessary new language to describe this kind of reality. That fractional index alpha literally indexing hidden dimensions, the eigenvalues lambda alpha marking coherence thresholds, that's new mathematical machinery.
And third, the physical revolution, showing how U1, SU2, SU3 arise naturally as eigenmodes without needing spontaneous symmetry breaking, proposing dimensional emergence via hyperfractal phase transitions, not compactification, and establishing that deep geometric field duality we talked about.
Okay, let's quickly contrast that with the old view just to hammer it home. Geometry. Standard physics uses mostly smooth, isotropic Riemannian space. FCHP uses anisotropic hyperfractal Finsler space, enabling directional resonance. Calculus. Classical smooth calculus versus fractal plus fractional derivatives, allowing for dimensional unfolding. Quantum states. Probabilistic wave functions versus geometric coherence eigenstates, unifying geometry and quantum behavior. Gauge emergence. Imposed symmetries needing breaking versus symmetries emerging naturally as solutions. A natural origin for forces.
Exactly. Each point represents a fundamental departure, leading to a potentially far more elegant and unified picture of reality.
So let's talk implications. If this holds up, where does it lead? Unified physics.
That's the biggest immediate hope. It offers a concrete path to integrate quantum mechanics, general relativity, and gauge theory under a single Finsler coherence formalism. The holy grail, really.
Yeah.
Finding that common ground between the very small quantum and the very large gravity, plus the forces. Coherence could be the key.
And gravity itself. You mentioned it's redefined.
Yes, potentially radically. Not as a force-bending spacetime, but as a coherent structuring principle arising from something called hypergravity invariance. It suggests gravity is intrinsic to the coherent structure itself, how reality organizes. It's not something acting on spacetime, it's a fundamental property of coherent spacetime, a deep structural aspect of the universe's resonance.
Wow. Okay, what about cosmology, the universe's origin and evolution?
Big implications there, too. The theory predicts hyperfractal dimensional unfolding during cosmic emergence. So the early universe might not have just expanded, it might have cascaded through dimensional layers, unfolding complexity as coherence organized itself.
A cosmic unfolding. That's a beautiful image. Does it help with any existing cosmological puzzles?
Potentially, yes. It might explain why early universe temperatures may not need to be extreme. If the initial state was already highly ordered through these coherence eigenstates, you might not need the incredibly hot, chaotic Big Bang conditions usually assumed to smooth things out. The ordering information could be inherent in the coherence from the start.
Okay, theory is one thing. But does this touch the real world? Any hints of technology?
The paper actually identifies potential resonance thresholds linked to future tech. It's speculative, of course, but intriguing. First, coherence-preserving computation, coheraputers. Computers harnessing these coherent states directly, potentially far beyond quantum computing.
Computing with the universe's own resonance patterns.
Right. Second, quantum energy extraction via coherence modulation. Could we tap into energy by manipulating these fundamental coherence levels, a new energy source based on modulating reality's structure? And third, next-generation navigation through hyperdimensional control. If we can access or influence these emergent dimensions, well, the possibilities for travel, communication are staggering. Science fiction territory, perhaps, but rooted in the theory's predictions.
Okay, so those are the far horizons. What are the immediate next steps for researchers working on this? How do they build on Lilien's paper?
The paper itself outlines crucial next steps. A full mathematical appendix is needed with all the symbolic derivations, stability maps for the eigenstates. That allows others to really dig in, verify, and extend the work. Also, a simulation framework is essential. We need ways to visualize this coherence eigenvalue spectrum to see how these states behave under different conditions.
Visualization seems key for something this abstract.
Absolutely. And Lilien proposes a toy model to help with that. The idea is to simplify things drastically, using maybe a 1D fractional Laplacian operator. Remember, at de Orfafse, the eigenvalues lambda and alpha in a simple 1D case might scale like non-PL. You add terms to represent the curvature and anisotropy inherent in Finsler space. The goal is to show explicitly how changing that fractional index alpha dialing through the dimensions causes the eigenvalues lambda alpha to cross thresholds, revealing the emergence of phases corresponding to U1, SU2, and SU3.
So the toy model would let you simulate dialing up a dimension and seeing, say, electromagnetism switch on when you cross a certain coherence eigenvalue threshold.
Exactly that. It would demonstrate the core dynamic. Changing alpha reveals hidden gauge phases. You'd see phase transition data emerge as alpha varies, maybe from 0.6 to 2.2, as the paper suggests. It makes the abstract concept concrete, testable, even in a simplified form.
What else is on the roadmap?
Connecting these eigenstates directly to that concept of hypergravity invariance is a major goal. And crucially, predicting measurable deviations from standard relativity. That's how you test it against experiment. And finally, developing an expanded visual codex. Imagine detailed diagrams, maybe even animations, showing the dimensional unfolding sequences. A complete map linking specific eigenmodes to forces, maybe even to phenomena like neutrino damping or dark matter phases, basically creating the visual language for this new cosmology.
A new map of the cosmos, drawn with the lines of coherence.
You could put it that way, redrawing our understanding based on resonance.
So wrapping this up, this deep dive into FCHP Coherence Eigenstates really paints a picture of a universe that's, well, fundamentally different. Not static laws, but dynamic emergence from resonant coherence. It feels more alive, more interconnected, a universe constantly composing itself.
It truly does. Lilien's work, earning that Tier 4 Eureka classification, shows how this specific mathematical framework, fractal calculus on an anisotropic Finsler manifold, doesn't just describe this emergence, it seems to govern it. It drives the appearance of fundamental forces, potentially unifies our disparate theories, all rooted in the geometry of coherence. It's a powerful candidate for a unified coherence theory of everything.
Which leaves us with a final thought, something for you to ponder. If our reality, from the smallest scales to the grandest structures, is truly this symphony of coherence resonance, what does that imply about our own place within it? Could understanding these deeper dynamics, these resonant patterns, eventually allow us to do more than just observe? Could we perhaps someday learn to consciously participate in the unfolding of reality itself? A profound thought indeed. Something to consider until our next deep dive.